I would like for you to imagine that you are a college student in the 1960s and that in need of a part-time job for extra money, you have become employed with a grocery store or with a store like Dollar General. A store like Dollar General back then would have been a place called Kresge's or Woolworth's. Your position with your new employer is a cashier. As a cashier in one of these stores, you would have to, as a customer came through your cash out line, have to put into the cash register manually each price of every item as it came by you. The items' prices were placed on the items in various different ways. As you can see here, the magnifying glass had its $3.29 price placed on the item with a sticker. Whereas in a grocery store, a half-gallon of milk would have the price stamped on it in black ink in one of these two locations, either maybe down here or probably more likely up here. Here was the problem with that system of pricing items. First of all, it was time-consuming for the cashier to have to be able to manually enter in the price of the item in the cash register, for one. Second of all, sometimes these prices got rubbed off of the item, so the person would get to the cash line and the price would not be on the item. Therefore, it would cause a delay. They would have to check on what the price of the item was and then cash the person out. And sometimes nasty people would change the prices on the items by rubbing them off of the item or pulling the sticker off of the item so that there was no price. And they would tell the cashier what the price was in hopes that the cashier would enter the wrong price and save them money. Well, as you can see, this was a problem. It was a problem for grocery stores. It was a problem for stores like Dollar General. They would lose money because of people cheating. They would lose time because it took a lot of time for cashiers to check people out. Then all of a sudden, a very sharp individual came up with a system that they could use to price items that could be scanned, and thus saving much time for the cashiers and the stores. This system that was developed was called the Universal Product Code, and you've seen these bars on every item you buy. And this Universal Product Code revolutionized how people get cashed out at the cash register in stores. Pardon me for reading to you, but let me read to you the history of the UPC code. On a Sunday afternoon in 1971, an IBM engineer stepped out of his house in Raleigh, North Carolina, to consult his boss who lived across the street. "I didn't do what you asked," George Lauer confessed. Lauer had been instructed to design a code that could be printed on food labels and that would be compatible with the scanners then in development for supermarket checkout counters. He was told to model it on the bull's eye-shaped optical scanning code designed in the 1940s by N. Joseph Woodland, who died last month. But Lauer saw a problem with the shape. When you run a circle through a high-speed press, there are parts that are going to be smeared, he says. So I came up with my own code. His system, a pattern of stripes, would be readable even if it was poorly printed. That pattern became the basis for the Universal Product Code, which was adopted by a consortium of grocery companies in 1973, when cashiers were still punching in all the prices by hand. Within a decade, the UPC and optical scanners brought supermarkets into the digital age. Now an employee could ring up a cereal box with a flick of the wrist. When people find out that I invented the UPC, they think I'm rich, Laurer says. But he received no royalties for his invention, and IBM did not patent it. Did someone mention a box of cereal? Well, here's a box of Lucky Charms. I don't know a single person who doesn't like Lucky Charms. Lucky Charms obviously is a cereal that is bought at the store every day. And you will notice that in Lucky Charms, there is on the bottom flap one of these UPC codes. Notice that this barcode and its associated numbers, in this case 12 numbers, make up the UPC, or what we call the Universal Product Code. The first 6 digits encode information about the manufacturer, and the next 5 digits encode information about the actual product. This leaves us with the last digit, in this case an 8, which is called the check digit. The check digit provides a means of detecting if the UPC code number is incorrect. So now let's take a look at how we check to see if this is a correct UPC code on Lucky Charms. All UPC codes must exhibit a particular configuration. And here's how that configuration works. First of all, you take the code in question and multiply the values of the numbers by 31, 31, 31, and so forth until you've completed them all. Once you've obtained the products of all those numbers, you simply find the sum of the results you obtained in the step prior, and the answer you get should be equal to 0 mod 10. So let's see if this configuration is satisfied by the example shown. So let's give Lucky Charms a try. So we'll multiply by 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, and 1. And let's draw ourselves a line here. Okay. Alright, so what are our products? 0, 1. Now notice here I get a 2-digit answer. So what I'm going to do in that case is I'm going to underline it. Alright, 0, 0, 0, 6, 7, 15, another 2-digit answer, 3, 12, another 2-digit answer, and 8. So why did I underline the 2-digit answers? Well, as you recall, we want to get the sum of all these numbers that we've gotten as our products here, and we want to see if we get 0 mod 10. Well, remember, these 2-digit numbers can be simplified into mod 10 numbers very easily by simply throwing away any digit except the units digit. So what I'm going to do with 18 is simply make it 8. With 15, I'm just going to make it 5. And with 12, I'm just going to change it into 2 because 18 is 8 mod 10, 15 is 5 mod 10, and 12 is 2 mod 10. Now what I will do is get the sum of all these numbers across the bottom of this huge multiplication problem. So I'll add 0, 1, 8, so forth. So that's 9, and 6 are 15, and 7 is 22, and 5 is 27, and 3 is 30, 32, and 8 is 40. And you will recall from our earlier discussions that any number that is a multiple of 10 has a value of 0 mod 10. 40 is a multiple of 10, therefore the answer to this problem is 0 mod 10, which tells us what? It tells us that this is a correct UPC code. Hey, look at this. Keebler Club Crackers, a real favorite at any party. I wonder if their UPC code satisfies the configuration of a correct code. So let's take a look, first of all, at the UPC code on the bottom of the box, and let's check it out and see if it actually works. So again, we multiply by 3, 1, 3, 1 going across, so 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, and 1. And drawing my line across the bottom here, to make it easy for me to multiply, I obtain the following. 0, 3, 0, 1, 0, 0, 12, again a two-digit number which I will underline, 9, 0, 5, 6, 4. And as we did before, I will change the two-digit number into a mod 10 number right away, and I will add to see if I get a multiple of 10. 3, 4, 5, 6, and 9 are 15, 20, and another 10 makes 30. So obviously again, I've gotten 0, mod 10, so this code definitely satisfies the configuration required for a correct UPC code. Notice we have here a bottle of Windex, and this is the product that was their original Windex. As we're going to see in a few moments, we're going to look at another Windex product. But notice in this Windex product, the UPC code has a number missing on the end, and of course that number is the check digit. And you'll notice I've replaced it with a letter X. Can we figure out what X needs to be to make this configuration be correct for original Windex? Well, let's give it a shot. So here we go. We'll multiply again by 3, 1, 3, 1 across. So 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, and 1. And drawing my line again, like so, I will have the following. 0, 1, 27, which I will underline because it's two digits. 8, 0, 0, 21. Again, a two-digit number underlined. 0, 6, 9, 21, which I will underline. And of course, 1 times x from algebra, you know, is simply x. So I will change this 27 to a 7, 21 to a 1, and this 21 to a 1. And so now I'm going to add across. 0, 1, 8, 16, 17, 23, 32, 33. So let me write this down. I have 33, and I have to add some number x to it from over here, so that my answer comes out 0 mod 10. Well, what would x have to be in order for us to get a 0 mod 10 answer? Well, you'll notice that x can only be a one-digit number. So it has to be a number between 0 and 9, such that when I add it to 33, it gives me a multiple of 10. Well, I think you can see that x has to take on a value of 7, because 33 plus 7 gives us 40, which is a multiple of 10. So this number up above here should be, our check digit, should be 7. Let's check it out and see. If I move this covering away, you'll notice that x is equal to 7. Well, let's try another Windex product. This is called Crystal Rain Windex. And notice its number is very similar to the last number we just checked, because it's made by the same company. Well, but however, this time I've done it a little differently. I have covered up one of the digits in the middle of the problem, right here. So let's see if we can determine what that missing value is. And you'll notice I've placed an X in its position on the numbers from the UPC code. So here we go again. Let's do our 3, 1. So 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, and 1. Draw our line again. And let's see what we obtain. 0, 1, 27, 8, 0, 0, 9, 1, 3x, 8, 24, and 1. Well, 27 is a two-digit number. I will make it a 7. 24 is a two-digit number, of course, which I will make into a 4 to make the problem a little easier for me. But notice this time I have a 3x here. So I bring my 3x down here, like so, and I add across 0, 7, and 1 make 8, 16, 16 and 9 is 25, 26, 26 and 8 is 34, 38, 39. So if I add 39 and 3x together, I should get 0 mod 10 if I pick the appropriate correct value of x. Now, this can be kind of a complicated feeling problem because we're dealing in modular arithmetic, but let's use a little common sense. Whatever value we put in for x and triple it, okay, it has to add up to a multiple of 10. And that multiple of 10 will make it 0 mod 10. X can only have values from 0 to 9. They can only be one-digit numbers. Well, what number could I put in here, single-digit number, that tripled ends in such a way that 39 becomes a multiple of 10? Well, I think you can see if I put 7 in here for x, 3 times 7 would be 21, and 21 and 39 added together gives me 60, which is a multiple of 10. So x has to be equal to 7. And you notice if we go up here and take a look, draw this over, the number that is up here is indeed a 7. Now let's say you couldn't see that. What if I just started with 0? 3 times 0 is 0. 0 plus 39 is 39. That's not a multiple of 10. 1 times 3 is 3. 3 and 39 is 42. It's not a multiple of 10. So I go to 2. 3 times 2 is 6. You see what I mean by trial and error. You can just keep trying the problem until you finally obtain the answer that you know gives you 0 mod 10. Well, now that you've had some experience with coding and working with mod 10 numbers, I would like to take a look at another application of using mod 10 arithmetic in our banking system. Notice this is a check for GK's tax service, and you'll notice that it is from the Kedmore Teachers Federal Credit Union, which is just like a bank. And you'll notice that there is a number written on the bottom of the check, right down in here, that begins with 222381112. That number, up to that colon, is called a bank routing number. Bank routing numbers have to meet a certain configuration in this country, in fact in the world. And bank routing numbers work a lot like UPC codes. Have you ever called in to buy something and they've asked you to read to them your bank routing number? Well, that's that number in the lower left-hand corner of your check. And you know, people might be tempted that aren't very nice to give a fake bank routing number. You know what? They can check this routing number very quickly. They have a database which has a listing of all the banks in the country by routing number. So if you give a routing number, they can pretty quickly tell whether or not you're giving them a false one. Also, bank routing numbers, as I said, have to meet a certain configuration, and it involves mod 10 arithmetic as well. So here's how the system works. The formula you use to multiply the routing number by consists of 739, 739, and another 739. Routing numbers are only 9 digits long. You add the answers to the multiplications you have just done, and you should get a sum of 0 mod 10. And just like the case of the UPC code, the last digit again is called the check digit. So the banks are actually identified by the first 8 digits. The 9th digit is the check digit that makes the problem come out 0 mod 10. So let's check out this credit union's bank routing number and make sure it meets the configuration required nationally. So we multiply instead this time by 739, 739, and 739. You can see that this pretty much works just the same way a UPC code works. It's the same basic principles. So let's see. We have 14, I'll underline it, 6, 18, underline it, 21, underline it, 24, underline it, 9, 7, 3, 18. And because these numbers are quite a bit larger in a lot of cases, I'm going to make sure I change them over to mod 10 numbers. 4, 8, 1, 4, and 8. Now I will add across, and I should get, hopefully, 0 mod 10, or a multiple of 10. So I add 4 and 6 is 10, 18, 19, 23, 32, 39, 42, and 8 is 50. Since I've obtained 50, we know that is 0 mod 10. So I'm all set. You can see that this bank routing number satisfies the required configuration. And I'm certain that you're not surprised to see that we can have problems similar to the ones for UPC codes. What is the check digit required to make this a correct bank routing number? Well, this is a very simple case because the numbers have a lot of zeros in them, but let's give it a try. So 7, 3, 9, 7, 3, 9, 7, 3, 9. And I'll draw my line again. And here we go. 0, 6, 18, 0, 0, 0, 0, 6, and 9C. Well, this will become an 8. So what is my equation going to be going across here? 6 and 8 are 14, and 6 is 20. So 20 plus 9C has got to come out 0 mod 10. Well, gee, this is already a multiple of 10. What would C have to be in order that when I got this product and I added it to 20, it remained a multiple of 10? Well, I think you can see that C has to be equal to a value of 0. Does anyone recall what this bank routing number is? Well, this was HSBC Bank, a very popular bank here in the Buffalo area for years, which took over for Marine Midland Bank and was also the bank name on the tower, or the largest building in Buffalo downtown, which is no longer called the HSBC Tower. So let's try one last problem. Let's find out what the check digit would be on this particular bank This is a very popular bank here in Buffalo as well. And let's determine the value of C here. So again, we use 7, 3, 9, 7, 3, 9, 7, 3, 9. And we draw our line, do our multiplication, 0, 6, 18, 0, 0, 0, 0, 12, and 9C. Of course, I have to underline 12. So I make this 8, I make this 2. So I'm going to have 9C once again in my formula. Okay, 6 and 8 is 14, 15, 16. All right. So 9C plus 16 has to be equal to 0 mod 10. All right. Well, let's see. What does C have to become to make this become a multiple of 10? Well, let's do it by trial and error. If I put a 0 in here for C, 9 and 6, or 0 and 16 would be 16. No good. 1 in there. 1 in times 9 is 9. 9 and 16 is 25. No good. So I put a 2 in there. 2 times 9 is 18. 18 and 16 is 34. No good. So I can continue my trial and error process. But I think you can see my number that comes out of this, my 2-digit number, is going to have to end in a 4 because of the 16 here. So the only number I can put in there that will give me a 4 on the end is C being equal to 6, because 6 times 9 is 54, and 54 plus 16 is 70. So our bank routing number is complete when this becomes a 6 down here. Do you know what bank this is? This is M&T Bank. Now, the only thing you must remember about doing these problems is this. For UPC codes that we will work on in class, you always use 31, 31, 31, 31, and so forth. For bank routing numbers, you always use the multiplication code of 739, 739, 739. Also, let me give you this tidbit of information. In class, we're also going to talk about credit card validation and configuration. And if you want, you can spend a few minutes going online and looking up how do banks protect themselves from phony credit card numbers using modular 10 arithmetic. The system is a little bit different than what we've seen, but we'll talk about it in class. Take care. We'll see you there.